Howdy, folks. This is Keith Wiggins with PAG Waste Management. Sorry for that long pause. It's been a busy week, but I'm excited to get back into Chapter 4 and finish it out today. So let's get started. This is the continuation of the Handbook of Biomass Downdraft Gasifier Engine Systems. We're on Chapter 4 and 4.2.3. We'll just reread this little section here just to go over it again. Biomass combustion is more complex than either pyrolysis or gasification, since the biomass must first pyrolyze, then be partially combusted or gasified before it is fully combusted. However, the overall global reaction of biomass combustion can be represented by the following equation, right? Where this CH1.40.6 is an average formula for typical biomass. The actual composition for specific biomass is shown in the tables 3.3, 3.4, 3.6, and 3.7. The nitrogen is shown in parentheses because it is an inert portion of air and does not take part in the reaction. For oxygen combustion of biomass, it would be omitted. This combustion produces 20.9 kilojoules when the temperature of the combustion product is low enough for all the liquid to be water, and this is the value that would be measured in a bomb calorimeter, calorimeter, and reported as the high heat of combustion, or HHV, as shown in table 3.6 and 4.1 below here. In most practical combustion devices, the water escapes to the atmosphere as a gas, and the heat of vaporization of the water is not recovered. In this case, the low heating value, LHV of 20.4 kilojoules, would be the maximum heat that could be generated. The difference between LHV and HHV is small for dry wood, but increases rapidly with moisture content of the wood. In the United States, the HHV is normally used for rating the efficiency of stoves. In Europe, the LHV is used. As a result, European wood stoves are typically quoted as 10% more efficient than comparable U.S. wood stoves. 4.2.4, chemistry of biomass gasification. The change in composition produced by air or oxygen gasification is shown in figure 4.1. Ideally, one would like to add the smallest amount of oxygen possible to carry the solid composition to the composition oxygen in figure 4.1, a mixture of carbon monoxide and hydrogen, according to the formula shown here. Unfortunately, there is more energy contained in the carbon dioxide and hydrogen than is contained in the biomass, so that this reaction would require the transfer of energy from some external source, which would greatly complicate the process. In practice, some excess oxygen must then be added for gasification, carrying the reaction to point O in figure 4.1b, right down here. Oh, sorry, down here. I'm losing it. Producing some carbon dioxide and water, according to the formula there. Typically, a few percent of methane are formed as well. Typical properties of producer gas from biomass are shown in table 4.2. So we have carbon monoxide, carbon dioxide, hydrogen, water, methane, nitrogen. And here are the gas high heating values here on the wet basis and the dry basis, the HHV and the LHV. Air ratio required for gasification. We have a few 2.3 kilograms of wood per kilogram of air. Air ratio required for gas combustion, 1.5 kilograms of wood per kilogram of air. Right, and so there's footnotes to these charts, and I'll let you guys go through those if you're interested. The ratio, carbon monoxide to carbon dioxide, or hydrogen to water, is a measure of the producer gas quality. Let me see if I can do this. Approximately 30% of the biomass is burned off to provide the energy for gasification of the rest. The exact amount of excess oxygen required depends on the efficiency of the process. It can be improved in practice with insulation, by drying, or by preheating the reactants. A fascinating question in gasification is how the reacting products know how much oxygen to use, and we'll see something below. So next section, thermodynamics of gasification. Thermodynamics is the bookkeeping of energy. Although thermodynamics cannot always predict what will happen for a particular process, it can rule out many things that cannot happen. It's interesting. It was mentioned above in the 4.2. Equation 4.2 is thermodynamically impossible in the absence of added heat, and that in 4.3 actually governs the reaction. How is this determined? At a high temperature where gasification takes place, typically around 700 degrees to 1,000 degrees Celsius, there are only a few stable combinations for the principal elements of biomass: carbon, hydrogen, and oxygen. These are carbon, carbon monoxide, carbon dioxide, CH04, hydrogen, and water. The relative concentration of these species that will be reached at equilibrium will be predicted from the presence or the pressure, the amount of each element, and the equilibrium constant determined from the thermodynamic properties and temperatures subject to an energy balance. It is then possible to determine the species that would form at equilibrium as a function of the amount of oxygen added to the system. The results of the calculation of this type are shown in later on figure 4.4 and 3.5. Here we go. The adiabatic reaction temperature of biomass with air or oxygen determined in this manner is shown in figure 4.4 down below. It is the temperature that would be reached if biomass came to the equilibrium with the specified amount of air or oxygen. There is no guarantee that equilibrium will be reached in any given gasifier, but downdraft gasifiers approach equilibrium quite closely, and we'll see that below. The oxygen used in a process determines the products and temperature of the reaction. The oxygen consumed is typically plotted as the equivalence ratio, the oxygen used relative to that required for complete combustion. Complete oxidation of biomass with oxygen requires the weight ratio of 1.476. A very low or zero oxygen use is indicative of pyrolysis, shown on the left of the figure. And combustion is indicated by greater than that one equivalence ratio at the right. Okay, so you're hitting pyrolysis on one side and combustion on the other. The composition of the gas produced is shown in figure 4.4b. The amount of energy remaining in the char and converted from solid to gas is shown in figure 4.4c. We'll get to all these. The low heating value of the gas is shown in figure 4.4d. From these figures, it is seen that an equivalence ratio of about 0.25 of all the char is converted to gas, and the fraction of energy in the wood converted to gas reaches maximum. With less oxygen, some of the char is not converted. With more oxygen, some of the gas is burned, and the temperature rises very rapidly, as shown later on in figure 4.4. Thus, it is desirable to operate as close to an equivalent ratio of 0.25 as possible. How is it possible to operate exactly at this ratio of 0.25 in a fixed bed gasifier, operating at lower values of the equivalence ratio would cause charcoal to be produced as far as a low equivalence ratio, and it would build up in the reactor unless it is augered or shaken out. Operation at values of the equivalence ratio above 2.5 consumes charcoal and the temperature goes up rapidly. Hence, maintaining the bed at a constant level automatically ensures the correct oxygen input. So indirect and direct gasification processes. We're in 4.3 now. So indirect pyrolytic gasification. It is now recognized that wood oil vapor is unstable at temperatures above 600 degrees centigrade and cracks rapidly at 700 degrees to 800 degrees centigrade to form hydrocarbon gases such as methane, ethane, and ethylene, hydrogen, carbon monoxide, and carbon dioxide. In addition, one obtains a 1% to 5% yield of a tar composed of polynuclear aromatics and phenols similar to those found in coal tar. Pyrolytic gasification is accomplished when a portion of the fuel or char is burned in an external vessel with air, and the resulting heat is used to supply the energy necessary to pyrolyze the biomass. The principal advantage of this process is that a medium energy gas is produced without using oxygen. The higher energy content may be required for long distance pipeline delivery. The disadvantage is that a significant fraction of tar may be produced and indirect heat or mass transfer is required, which complicates the apparatus and the process. Pyrolytic gasification will not be discussed further because it is only practical in large installations and is not well behaved and is not as well developed as direct gasification with oxygen or air. So here we get to direct gasification. Pyrolysis and gasification processes are endothermic, so heat must be supplied in order for the process to occur. In fact, the heat required to accomplish pyrolysis and raise the products to 600 degrees centigrade is about 1.6 to 2.2 kilojoules, representing 6% to 10% of the heat of combustion of the dry biomass. This heat is supplied directly by partially combusting the volatile tars in the downdraft gasifier. In updraft gasifiers, it comes from the sensible heat of the gases resulting from charcoal gasification. This combustion then dilutes the product gas with carbon dioxide and water. The products of combustion with oxygen. If the combustion is accomplished with air, the gas is also diluted with about 50% nitrogen from the air. The principal advantages of direct gasification are that the one-stage process is very simple. The direct heat transfer from the gases to the biomass is very efficient, and the process is largely self-regulating. If air is used, the resulting gas is diluted with atmospheric nitrogen to a producer gas value of this 5,800 to 7,700 kilojoules per nanometer squared. When oxygen is used for gasification, a medium energy gas is contained 11,500 kilojoules per nanometer squared. Medium energy gas can be distributed economically for short distances. And here's the chart 4.4 that we were talking about earlier. Shows different with heat, low heat and equivalence ratios, and heat and temperatures and equivalence ratios. So we were medium energy gas can be distributed economically for short distances up to 1 mile in pipelines. It is also called synthesis gas, since it can be used as a feedstock for chemical synthesis of methanol, ammonia, methane, and gasoline. The oxygen must be either purchased or produced on site, making it economically prudent only in larger installations. It has been reported that pipeline distribution of low energy gas is also economically practical for distances up to 1 mile, if the air used for the gasification is compressed rather than compressing the larger volume of producer gas. There are many types of direct gasifiers, each with its special virtues and defects. They will be discussed in Chapter 5. Yeah, we'll get into that. So Figure 4.5 is a schematic diagram of an updraft and downdraft gasifier showing reactions occurring in each zone, right? Right, so interesting. So this is the updraft gasifier, this is the downdraft gasifier. So 4.4, principles of operation of direct gasifiers. And then this will be closing out here. Actually, let's stop right here at 4.4 so that I can get some more notes for you. This is going to be long enough for today. Thank you for sticking with us and going through those complex items. I might have individual cast just directly for Figure 4.4 to talk about some of these diagrams here. So I will talk to you later. See ya.